This recent paper that I wrote with Nati Seiberg in July. The talk will also be based on another upcoming paper with Nati and Shu-Heng. I decided to do an iPad talk because I think a lot of the things I'm going to talk about are quite explicit and the calculation can really be done almost in real time. So it's good to do it in an iPad way. But because of that, I won't be able to provide a very complete reference list. I'll try to mention a lot of the related work, but for the complete reference list, please see our paper here. We try our very best to include all the related papers. Okay, so I prepared a little bit too much materials. I'm just going to jump right in. So in recent years, there has been a lot of discussions of non-invertible symmetry. I'm not going to do a general overview or introduction to that, but let me just mention that arguably the simplest example in the context of quantum field theory is the one plus one D Ising CFT, which is also arguably the simplest quantum field theory of all. There has been a lot of discussion of the Cramer's one-year symmetry, which is implemented by a conserved operator, or in Euclidean signature, a topological line D. It obeys the famous algebra that D times D is 1 plus eta, where this eta is the ordinary invertible Z2 symmetry of the Ising model. There are two more equations. Let me just quickly write them down. And eta being a Z2 symmetries means that eta squared is 1. What's interesting about this object D is that it's not invertible. There isn't an inverse such that D times D inverse is just 1. That statement has to be qualified a little bit more. But let me also point out the fact that D as a conserved operator in the continuum, D is its own dagger. However, D times D dagger is not 1. So it really goes beyond the standard paradigm by Wigner. All right, but that's not what I'm going to talk about today. Today, I would like to consider a particular microscopic realization of the Ising CFT, which is the transverse field Ising model, right? TFIN, or its abbreviation. This is a lattice model that I will focus on. It's also arguably, it's probably the simplest many-body system. And the question that we are going to explore or discuss today is what aspect of this non-invertible symmetry is there already in this particular microscopic realization of the Ising CFT. So let me give a very quick review of the transverse field Ising model. You can also look it up on Wikipedia. So it's a lattice model in one spatial dimension. To talk about its symmetry, it's standard to put the system on a closed chain. At least that's what we usually do in the continuum conformal field theory. So I'm going to draw a circle here, which will be my space. There will be a time direction soon. So this is my one-dimensional space, which is a periodic circle, and it has n sites. I'm going to index the sites by j. So j equals to 1, 2, 3, all the way to n. I'm going to start with the periodic boundary condition. I won't say too much about the anti-periodic one. It's discussed in our paper, but let's start with the simplest boundary condition. So I'm on a closed periodic chain of n site. There's a qubit at every site. So at every site, we have a spin up, spin down, and the Hilbert space is just C2 for each J. And since I'm on a closed periodic chain, the index J throughout the talk will always be identified with J plus N. I'm using the convention that a tilde sign means identification. All right. So it's a very simple finite dimensional system if I take n to be finite, which will be the case for most of the talk. For any finite n, the total Hilbert space is finite dimensional and it's a tensor product Hilbert space. With dimension 2 to the n. So it's a system you can really put it on Mathematica on a computer and solve it exactly. Since I have a qubit at every site I can consider the Pauli operator. Xj and Zj. They obey the algebra Xj, Zj equals minus Zj, Xj. Each one of them squares to 1. And if the Pauli operators at different sites will commute with each other. All right, so that's the setup. Let me emphasize this is a tensor product Hilbert space. So I haven't talked about the Hamiltonian yet. So far, I've only introduced the Hilbert space and the local operators acting on this Hilbert space. The Hamiltonian that we will talk about is the Ising Hamiltonian. In the paper, we also consider deformation of the Ising model, preserving the symmetry of interest. But for simplicity, let me focus on the Ising Hamiltonian. But I want to stress that a lot of the discussions and conclusions will hold for the more general deformed Hamiltonian. All right, so this is the standard Ising model Hamiltonian with the coefficient G. And when J is N, I use the identification to bring it back. So N equals to N plus 1 will be identified with 1. Now the Ising model has the famous phase diagram. So by a Fourier definition, I can always take G to be positive. Then the phase diagram looks as follows. When G is very small, you can ignore this term. And then we just have the nearest neighbor interaction. And this is in the older phase. Because the eigenvalue of Z could be O plus or O down. In the opposite limit, when G is very large, then you want the eigenvalue of X to be plus 1. That's the disorder phase. But here, the symmetry is spontaneously broken. Right at the critical point where G is 1, we have the, in the thermodynamic limit, it becomes the Ising CFT. Now let's analyze the symmetry of this model. For any G, there's a Z2 global symmetry. That's just a standard Ising flip symmetry. So I'm going to denote the charge operator or symmetry operator by eta, which is nothing but the product of the xj's. So obviously this commutes with the Hamiltonian here because every z appears in pairs in the Hamiltonian. We have eta squared being 1 and eta h, the Hamiltonian is h eta for any g. And for any g, we see how do I organize this a little bit better. For any g, we also have a lattice translation, which will be important later on. I'll denote it by t. You can write down the operator t very explicitly in terms of the Pauli operators. It's in the paper, it's in a lot of references. I'm not going to write it down. What matters is how it acts on the local operators. And this is true for OJ. Again, let me emphasize that J is identified with J plus N. So at a generic G, these are the two symmetries that will be of interest to us. There's a Z2 global symmetry and a lattice translation. The Z2 in the continuum limit goes to the Z2 of the CFT or of the gap quantum field theory, depending on where you are on the parameter space. And the lattice translation will go to the exponentiation of the continuum translation. The question we would like to ask in this talk is what happens at g equals to 1? So let me put the question here. And many people have asked this question, even starting from the time of Kadanoff, but we are going to formulate the question in a slightly different way. We ask, at g equals to 1, the critical point, is there an operator of the TFI, the transverse field Ising model, such that I'm going to write down a list of conditions that I want these operators to satisfy. Now, the zeroth order condition I would like to impose should already be implied by what I mean by an operator. And by an operator, I really mean it's an operator acting on the 2 to the n dimensional Hilbert space that we started with, H. I don't want to make the Hilbert space any larger. I don't want to make the Hilbert space any smaller. It's literally the original 2 to the n dimensional Hilbert space that I wrote down here. And by an operator, I mean something that map H to H itself. That's the zeroth order condition I want. The next one is that I want it to be a symmetry. So the minimum requirement for a symmetry is that it commutes with the Hamiltonian.
May I ask a quick question?
Yes, please.
So is the claim that even at finite n, there's something special about g equals 1? Or
yes.
Okay.
Well, I haven't made that claim yet, but that's where I'm heading.
Okay, thank you.
Yeah. Okay. And the last conditions is that I want it to become the Kramers-Wenier symmetry D of the Ising CFT. And I'll clarify what I mean by become when we take the thermodynamic limit. Okay. So this is the list of conditions that I want this operator to satisfy at G equals to 1 of the transverse field Ising model with finite n. Now, the first two conditions are stated for finite n. The last ones is a statement of the limit of this operator when we take the thermodynamic limit.
Sorry, can I ask a question?
Yes, please.
But in the n equals to infinity limit, the Kramers-Vannier-Edwards defect should map the Hilbert space to the twisted sector, right?
Well, that depends on what we mean by map.
So do you mean that D is really an operator in the sense that it acts on the Hilbert space by mapping the Hilbert space to itself?
So let's start with the continuum. In the continuum, you can really, as I say, you can really treat the D as an operator acting on the Hilbert space, the untwisted Hilbert space, let me emphasize, to the untwisted Hilbert space. And this map has a kernel.
Oh, I see. Okay.
What you have in mind is something more general, which I will not talk about here, which was not discussed here, and we might say something about it here.
So basically, you can define this D also by taking the direct sum of all twisted sectors and then projecting on the untwisted sector. So whenever you are mapping an operator to the untwisted sector, you will declare the D acts by sending it to 0.
In this talk, I'm just going to focus on this particular.
Okay.
Yeah, I'm not going to extend it.
I see. Okay, thank you.
But I kind of secretly will do, but at the end of the day, it's just this. All right. Any other question for the setup of the problem? All right. Okay. Now, if you ask this question to someone on the street, then the person would say, well, at G equals to 1, the Hamiltonian obviously has a new quote-unquote symmetry. And what is that symmetry? Let's take a look at this Hamiltonian. When G is 1, these two terms are on the same footing. And the pedestrian would say that there's a symmetry mapping the x term to the zz term and the zz term to x. And let's try to write it out. After all, that's how we first learned symmetry in kindergarten. What is a symmetry? You look at the Lagrangian, you look at the Hamiltonian, and you figure out some transformation that leaves the Lagrangian or Hamiltonian invariant. That's before you learn anything about Noether current, conserved operator, topological defect. So if you just hand this Hamiltonian to someone at G equals to 1, then obviously there's a symmetry exchanging this two. And what is that transformation? At G equals to 1, H is invariant under Xj to Zj, Zj plus 1, and Zj, Zj plus 1 to Xj plus 1. And as many of you might have already expected, this is nothing but the Kramers-Vannier transformation. Now, a very distinguished physicist once told me not to write any arrow in a physics paper. And I think this is a perfect example for that quote. So you can ask, what does this arrow actually mean? In particular, is the arrow implemented by a unitary operator? That's what we usually mean by a global symmetry. But in this particular case, you immediately see that that's not possible. Because suppose there were such a unitary operator that implements the arrow. But if there was such a U, then let's compute U eta U inverse. Let me remind you, eta is the non-trivial Z2 symmetry operator of the Ising model, which is defined as the product of J from 1 to n xj u inverse. And since use has an inverse, you can then act on the individual xj factor and use this transformation rule to write this as zj plus 1. But then every single zj on a periodic chain appears twice. Therefore, using the fact that zj squared is 1, you get 1. But that means eta is 1, which is clearly a contradiction. The Z2 operator acts non-trivially on our Hilbert space. So this very simple-minded argument immediately tells you that the Kramers-Wenier transformation cannot possibly be implemented by a unitary operator. This is a well-known fact. And that means there's something misleading in writing the arrow. Now, I'm going to tell you the precise.
Excuse me.
Yes, yes.
Hi, Shu-Heng.
Yes.
Where did you use the unitarity condition for you?
Well, I actually didn't. I just used the fact that there's an inverse.
So the question should be better phrased as whether there is a U which there exists an inverse.
I think I agree, but phrasing it in terms of unitary is a weaker statement, and it's also true. The fact that there isn't such a unitary operator.
Okay.
It's quite interesting that so far all the questions come from the local Stony Brook people.
Shu-Heng, may I ask another question?
Okay, for a change, great. Hello.
Hello. So
Yes.
do you only consider periodic chain boundary conditions in this case? So you don't have
In this talk, due to the limitation of time, I will only talk about the periodic chain. In the paper, we talk about anti-periodic chain as well.
Okay, thank you. Yeah.
Thank you. All right. Well, but the Hamiltonian is invariant under this transformation. So the question is, what implements this? So now let me write down the operator that does the job. So instead, let's consider the operator D. It's going to be a little bit complicated and non-intuitive the way I present it, but I want to present the answer first. And for the rest of the talk, I'm going to derive it. There are several factors. First, I'm going to put in a square root 2. Actually, this square root 2 is somewhat conventional. And because of that, I'm going to write it in a very light gray color so that you will probably neglect it. There's another factor which is not terribly important. It's a phase, which I also write in gray, meaning that don't worry about it too much. I think there's definitely something deep about the root 2, but for the scope of this talk, I will not say too much about it. I'm just going to write down some operator. And as far as the operator is concerned, I have the freedom of rescaling it for my convenience. But that's not going to be the full story, but I'm not going to say too much. All right, so the rest of the term takes the following form. I have a product from j equals to 1 to n minus 1. And by product here, I mean, it's an order product. Since we're taking product of non-commuting objects, so here, what I really mean by product is that I order them in the following way. Okay. Then there's another piece that takes this form. And finally, actually, I'm going to write this piece in red. All right, so that's the operator. It's quite complicated. It's not supposed to be intuitive at this stage, but it's very explicit. It's written in terms of the xj's and zj's. If you have 2 minutes, you can literally put this operator on Mathematica for any finite n and compute all its properties. let me say a few things about this operator. This piece, let me call it UKW, has featured in many papers in the past. I'm not going to make a complete list of references, but let me just say the most recent papers that has this, well, maybe not even the most recent paper, but one of the papers that talk about this operator very explicitly recently is a paper by Shu-Heng and collaborators in the context of sequential circuit. This operator is unitary. It's very easy to verify that each individual term here is a unitary operator. It's invertible and it's unitary. And obviously the phase is unitary. The root 2, as I said, don't worry about it too much. The part that makes it funny is the last term. This last term is a projection operator of the Z2 symmetry. So recall that the product of X is just the Z2 operator. So this is a projection down to the Z2 event subsector. So we already see that this operator does not have an inverse. What kind of algebra does this operator obey? We already have two players in the game. A
Juven
Z2
has a
symmetry.
question, actually. Juven,
Yes.
why don't
Oh,
you just
hi,
unmute
Juven.
yourself?
Yeah, Juven.
Hi, thanks, Shu-Heng. Just make sure there's a unitary phase of a Ma-A phase, and that n-dependent n is the number of sites.
Yes, the n is the number of sites right here.
So can you clarify that there's a Z8 kind of a U1 phase, Ma-A class of a U1 phase there?
Yes. So it is intimately related to the mod 8 anomaly of the Majorana theory, which I will talk about later on. But at this stage, it's just a choice of the phase that will make the algebra I'm about to write down look pretty.
Okay.
In the paper, we have a very extensive discussion of how to choose the phase appropriately. But in the interest of time, I probably won't say too much during the talk.
But because that phase is unitary, so E also has an inverse. So even I don't have that phase, does it affects the mean of D?
No,
Right.
but you will introduce some phase in the algebra that I'm about to write down.
Okay, thank you.
So at this point, it's just a cosmetic choice.
Right, thanks.
But yeah, thanks for the question. Okay, so let me write down the algebra. So what happens when you take D times D on the lattice? And let me emphasize again, this is really a calculation you can do very explicitly. You can take n to be 1 or 2. So maybe 2 maybe 1 is too degenerate. Then we're just talking about really, just 4x4 matrices. So D times D turns out to be 1 plus eta times the lattice translation. This is probably the most non-trivial relation. The other ones are easier. You see there's a Z2 projection here. So that means if D times eta is going to be the same as D, and similarly, if you multiply it the other way around. Lattice translation raised to the nth power is 1 because we have n site. Now, obviously, the Z2 operators commute with the lattice translation because the Z2 operator is a product of over all the x's along the lattice. What's more interesting is that this D operator also commutes with the lattice translation, which is not manifest. If you look at this expression, I pick a reference starting point, 1. But there's nothing absolutely special about site 1. We are on a periodic chain. Every site is on the same footing. But this expression does not make it manifest. I start with site 1, and at the last site, I also did something funny compared to the intermediate site. And indeed, UKW is not translationally invariant. But only when you multiply it by the projection operator will it be translationally invariant. And this operator D implements the arrow we were saying here, meaning that dxj give you zj plus 1d. And d zj plus 1 give you xj plus 1 times d. But you cannot move the d to the other side because there is an inverse. This d is a non-invertible operator. And at g equals to 1, it's a non-invertible symmetry of the transverse field Ising model because it commutes with the Hamiltonian. However, if you go away from the critical value, it will no longer commute with the Hamiltonian.
Hi, Shu-Heng. One question.
Yes.
The U KW commutes with the Hamiltonian?
No, it doesn't, because
Okay.
because there's a mistake at one site. It does not obey this equation.
So I see that it doesn't commute with the translation operator, but maybe it was not clear, so clear that it doesn't commute with the Hamiltonian. But yeah,
It's not clear the way I wrote it, but you can work out the way UKW acting on the XJ and ZZs, and you'll see that it doesn't preserve the Hamiltonian at one site.
okay.
So it's really necessary to have a projection here. It's not just for the sake of translation symmetry of the operator, but it's also for the fact that UKW is simply not a symmetry of the Hamiltonian on a closed chain.
Yeah, it just seems a little bit weird because eta, the C2 symmetry, does commute with the Hamiltonian, and the identity commutes with the Hamiltonian, but somehow the U double and the D commutes with the Hamiltonian, but somehow yeah, I mean, it's just a complete, but I will check it. Thank you.
The reason you have that, the reason it's non-intuitive is because if you have a symmetry A and a B, and both are invertible, and you have a symmetry C, typically you can invert B to the other side. So if you know C is a symmetry, B is a symmetry, then you conclude that A is also a symmetry. Here, what's different is that this guy is non-invertible. So you cannot bring it to the other side and conclude that U is a symmetry.
Thank you.
And thanks for that question. I should have probably emphasized that more, because it really underlies the fact that D is non-invertible, but it also cannot be written in terms of the other invertible operators, invertible symmetries of the system. You cannot say it's a derivative object out of the invertible U symmetry U and 1 plus eta, because U is not even a symmetry.
Sorry, the notation UKW seems to suggest that it has something to do with Kramers-Vanier, but can you clarify what is the relation?
Well,
any?
Yeah, so U implements the Kramers-Vanier transformation, except for one site that I didn't write down.
Or do you mean that it fails to be the Kramers-Vanier transformation only on one site?
It depends on what you mean by Kramers-Vanier, but it does not obey this relation at one site.
So on the open chain, it will be the Kramers-Vanier, Kramers-Vanier symmetry.
On the open chain, you have to specify the boundary condition for me.
Sure.
In fact, on the open chain, there's no way for you to have a symmetry D. You will, because you see, you always shift the lattice to the right by one side. So on the open chain, you get stuck towards the end.
I see.
Okay.
I have a question.
Yeah, please.
It's Tim from Dura. So if you project to the neutral sector, and then it's a genuine symmetry, correct?
If I project to the Z2 even sector, then this factor is trivial, and then D up to that unimportant factor √2 is invertible.
Right. But
however, as I emphasize, so that's why I put the condition here at the zeroth order condition.
I see. Okay. But I mean, that's like gauging Z2, or it's actually like gauging in time, right? Only Z2.
I would say it's not gauging Z2, because gauging is not just projecting to the Z2 even sector. It consists of the second step. But you are right in the fact that D is intimately related to gauging, and that will be further elaborated in an upcoming paper.
Okay, thanks.
Yeah, thank you. The equation I want to highlight here is this one. Already we see that it's different from the continuum one. So I use the curly D for the continuum operator. On the lattice, it mixes with the lattice translation T. And I will come back to that later. But at this point, I should probably move on to derive this operator for you. And later on, I will come back to this algebra and say much more about it. Okay. So how do we derive this operator D? How do we understand it intuitively? Well, to proceed, we would like to consider a different model. So we're taking a slight detour, but it will lead to the answer we want. So bear with me for maybe the next 5 minutes. So we're going to consider a different model. Consider the Majorana chain, or AKA the Kitaev chain. It's a different lattice model. It's not defined on a bigger circle, so I'm going to draw the circle bigger. I use a different index L. It's exactly twice as large as the Ising chain we had before, because I have 2 n sites here. In the paper, we also talk about the case when there are odd number of sites, but in the interest of time, I won't do it here. So in this model, we have a Majorana fermion rather than a spin. Majorana fermion, chi L at every site. L. They obey the standard Clifford algebra. Now the Hilbert space, well, do I want to talk about it now? Yeah, the Hilbert, no, let me get to that in just a minute. The Hamiltonian that I'm going to be interested in, actually 2 Hamiltonians, are the nearest neighbor interactions plus or minus chi 1, chi 2n. Well, let me emphasize that my L index, again, is identified with 2n. All right, so what just happened? We have 2n Majorana fermions in this new lattice model. So far, it has nothing to do with Ising. I consider 2 kinds of Hamiltonians. Both are nearest neighbor interaction. The H plus is the one with periodic boundary condition. So it's the same sign as the rest of the term. H minus is the one where we flip the sign at the last term here. Okay, so these are 2 different Hamiltonians. And we can, and the same comments applies here into the Majorana chain, that we can consider deformation of this model, and we did. But I'm not going to write those deformation down in the talk. There are, again, 2 symmetries of interest to us. The first one is the fermion parity symmetry, which I'll denote as -1 to the f. It's a product of all the chi's with a convenient factor of I to the n. What it does is that when it acts on the local fermion operator, it flips the sign. That's obviously symmetry of the Hamiltonian because everything is quadratic in chi. The I to the n is inserted such that -1 to the f square is 1, but don't worry too much about it. Now there's a second symmetry, which is the Majorana translation symmetry. This is to be distinguished from the Ising translation. I mean, after all, it's a different model at this point. So we have a translation symmetry for H plus. That's obvious. It just maps the fermion to the next site. And if you raise the translation symmetry to the 2nth power, not n, but 2nth power is 1. What's slightly non-trivial is that even the model with a minus sign here has a translation symmetry. All you have to do is to put an extra sign at the very last site. So for most of the sites, it just shifts L to L plus 1. And for the very last one, it takes it to minus chi1. And it's very easy to show that this H minus Hamiltonian is invariant under this lattice translation symmetry. And if you raise T minus to the 2nth power, it gives you the fermion parity. Okay, simple enough. So these are two models of fermions that we're going to consider, and the symmetries are the fermion parity and the lattice translation. There's an interesting algebra obeyed by them. This has been discussed by many people. There's a paper by Ian Affleck and collaborators. There's also a paper by Ting Shea, Tarun and collaborators. They study the algebra between the fermion parity and the Majorana translation. Let's compute T plus minus 1 to the F, T plus inverse. This is really a simple calculation we can do in real time, so bear with me. Minus 1 to the F is defined here. What T plus does is to move all the chi's to the next site. So it becomes chi2, chi3, to chi2n, and then chi1. But then this is not quite the original minus 1 to the F. So you have to bring the very last guy, the chi1, all the way to the beginning. I have even number of fermions here. So excluding chi1, I have odd numbers of them in the way. So as I bring chi1 all the way to the beginning, I get a very important minus sign. If there is a single most important minus sign in the whole talk, that's going to be this one. All right, I hope everyone is with me in this very, very simple calculation. It's very simple, but this minus sign means something very deep. In the continuum, it corresponds to an anomaly of the Majorana CFT, which we discussed extensively in the July paper. But for now, let me not make that connection. It's just a minus sign. It's not hard to convince you yourself that if you consider T minus instead, then there is no minus sign because you get the extra sign from T minus. All right, so that's it about the Majorana models that we want to talk about. There's a fermion parity, there's a Majorana translation symmetry. The Majorana translation symmetry is roughly a Z2n symmetry, at least for the periodic boundary condition. In the anti-periodic case, there's a more interesting algebra. In the periodic case, the important message is that the lattice translation does not commute with the fermion parity, the anti-commute. So that's the detour. Now let's try to make contact with the original question of the Ising model. Now, many people, so we hear the statement very often that Ising equals Majorana. This equality is in a way locally true, but the whole point of the talk today is about the global symmetry. So we have to pay more attention to what this equality means. And all the non-trivial facts come from these equalities. So let me put the quotation marks. Let me also make the color gray. And let me also put a question mark. And we'll see a lot of subtleties that follows. On the lattice, when people usually say Ising is the same as Majorana, what do they mean? They usually thought about the Jordan-Wigner transformations. So what's the Jordan-Wigner transformation? You start with the Majorana, and you pair up the L equals to 1 and 2 Majoranas, the L equals to 3 and 4 Majoranas, and so on. And because here I assume there are even number of sites for simplicities, the pairing is perfect. And then for each pair, I can do the following change of variables. So the standard Jordan-Wigner transformation reads, it's probably the inverse Jordan-Wigner transformation. So some of you might want to complain that I'm not being consistent with my notation, because in the icing discussion, I use X and Z, but here I use sigma X and sigma Z. There's a minor distinction between them, which I will talk about. So what did I just do? I take a pair of fermions and write them in terms of the Pauli matrices. This is so far is just a change of variables. The non-trivial claim is that the Clifford algebra obeyed by the fermions are compatible with the Pauli algebra obeyed by the sigmas under this equality. So there's nothing fancy here, it's just a change of variables. It's a non-local change of variables though, because a local fermion operator is now a product of a lot of the Pauli operators across the whole chain, or across part of the chain. Okay, so you can check that this is compatible with the algebra. Now written in terms of the new variables, what are our Majorana fermion Hamiltonians? It's a one-line algebra. And what people usually say is that this gives you the transverse field Ising model Hamiltonian. And indeed, you almost get it right for most of the terms, except for one site, or one link, I should say. So for most of the terms, you get a transverse field Ising model, but at the nth site, you made a mistake. Let me remind you, -1 to the f is I to the n, chi1 all the way to chi2n, which if you use the above change of variables becomes sigma 1x all the way to sigma nx. So -1 to the f written in terms of the sigmas is a non-local operators. The rest of the terms are completely local, but the last term is non-local. So if you just use the change of variables from Jordan and Wigner at face value, you start with a local fermion Hamiltonian, but you end up with a non-local bosonic Hamiltonians written in terms of the Pauli matrices. Now, of course, this term was well known in human civilization. I think already in the 1961 LSM paper, they pointed out that there's one mistake at the very last site you will make under Jordan-Wigner transformation. But our goal is to connect to the Ising model. So we're not done yet. If you just perform the Jordan-Wigner transformation, you didn't get the Ising model. So we have to do one more step. So to put it differently, we have to do Jordan-Wigner transformation globally. To do that, and that's the reason we have to consider both boundary conditions in the fermion problem. For each one of them, we have a Hilbert space. So I use curly H for the Hilbert space, which probably looks very similar to my Hamiltonian. Each one of them is 2 to the n dimensional. They're isomorphic. So to proceed, I'm going to take the direct sum of the periodic and the anti-periodic boundary conditions. So now I have a bigger Hilbert space, which has a tilde on top of it. And that's the direct sum of the anti-periodic Majorana chain with the periodic Majorana chain. So now the dimension of H tilde is 2 to the n plus 1. In this bigger Hilbert space, I have the Hamiltonian H tilde, which is H minus on the upper corner and H plus at the lower corner. All right. In this bigger Hilbert space, in this bigger system, we have a quantum symmetry, eta tilde, which is just acts as 1 on one block and -1 at the other block. It's related to the quantum or dual or orbital symmetry in the continuum. So in this bigger Hilbert space, we have a Z2 cross Z2 generated by eta tilde and -1 to the F tilde, which is just -1 to the F in each block. And let me make a quick comment that this Z2 cross Z2 is related to the categorical symmetry by Wen-Jie and Shao-Gang and other collaborators.
Sorry, can I ask a question?
Yes.
But I've not understood whether these two Hilbert spaces are different twisted sector for the Z2 symmetry or not.
Sorry, I didn't.
The H plus or minus are two different twisted sectors.
These are just two isomorphic copies of the of a 2 to the n dimensional Hilbert space. Plus and minus are just for my convenience of labeling them.
Yeah, what I'm asking is whether the Hamiltonian with minus can be understood as the Hamiltonian that you obtain from the one with plus by twisting
absolutely
with a line for the Z2 symmetry.
Absolutely, yeah. Thank you for that question. So you can view the H minus as from H plus with a -1 to the F twist. Absolutely.
So essentially, if I start from H plus and I consider the Hilbert space associated to it, H plus and minus are the two twisted sectors for the Z2 symmetry.
No, I would say H minus it can be viewed as the twisted sector from H minus. Wait, did I say the other way around? H minus is twisted sector of H plus and vice versa.
Yeah. So
they differ by a twist. That's all that matters.
So when you take the direct sum of the two Hilbert spaces, you are putting together the two twisted sectors. So this is why you have doubling the symmetry, right?
You can I'm putting together the untwisted one and the twisted one.
So but these like, should I think about it as a relative theory or it's
yeah, I think that's the right way to think about it, but I'm not going to use that term.
Okay, so it's
there's a second step. I'm not done yet.
Okay, thank you.
Sorry, as a follow-up to the previous one.
Yes.
Is this essentially a lattice version of ungauging spin structures, which we need to do in the CFT version of the two models?
It's a lattice version of bosonization.
Right. Okay, thank you.
Yes. But I'm not done yet. This is the first step. I'm not done yet because even if I double the Hilbert space, I haven't got rid of the non-local terms. So there's a second step. So this is the first step. In the second step, I'm going to do a projection. I'm going to project to -1 to the F equals to +1 sector in H minus. -1 to the F equals to -1 sector in H plus. So why do I want to do that? In H plus, if I project to -1 to the F being minus, then I make this term on the same as the rest of the terms. Conversely, in H minus, if I project to -1 to the F equals to +1, then I make this term on the same footing as the rest of the terms. So if I restrict to this projected Hilbert space, then my Hamiltonian becomes the same as the transverse field Ising model.
Shu-Heng, can I ask a quick question?
Yes.
So this H plus that you get after this naive Jordan-Wigner transformation on the Kitaev chain, is that related to the transverse field Ising model up to a conjugation by UKW?
Oh, that's an interesting question. I think the answer is yes, but I haven't done the calculation. But I think the answer is yes. UKW will create an eta line, basically.
Yeah, because it undoes that fermion parity line, right, on the last slide.
Yeah, yeah.
So does that have some meaning in this context, this fact?
I'm sure everything is related, but let me stick to the local Hamiltonian throughout the talk. And yeah, but I think I agree with you. I think that's correct. Okay, so once I've done this projection, So I want to make this projection so I can write it more succinctly as saying that well, this element of the Z2 cross Z2 in the bigger Hilbert space has to be +1. So that's the projection I'm going to do. So I'm going to call the projected Hilbert space H without the tilde. And H is now 2 to the n dimensional. So in the first step, we double the Hilbert space. In the second step, we reduce it by half. So we get back a 2 to the n dimensional Hilbert space, but it's kind of a linear superposition of the various sectors we had early on. Now let's look at the Hamiltonian. If I look at the projected Hamiltonian, it now takes the form of the transverse field Ising model, where this capital X and capital Z's are related to the sigmas in the following way. But don't worry about it too much. That's why I use different notations, symbols for them. Okay. So after a long song and dance, we finally get back the critical Ising Hamiltonian. And that's the precise relation between Majorana and Ising. That's what this whole thing is about. But why did we go through all this? The reason we went through all this is that we wanted to ask the following question. In the Ising model, there's a lattice translation, and its nth power is 1. In the Majorana model, there's a Majorana translation whose in the periodic sector whose 2nth power is 1. What happens to it? We don't have a Z2n symmetry in the Ising model. We only have a Zn lattice translation symmetry in the Ising model. So the whole purpose of going through this exercise is to track what exactly happened to the Majorana translation. And that's what we're going to do now. It's easier to consider the square of the Majorana translation operator. So I just put t minus square, t plus square here. Let me remind you, everything with the tilde acts on the 2 to the n plus 1 dimensional Hilbert space. All right, so this is an operator. And if you do the projection, it becomes the Ising translation. And there's nothing in tension with the projection because t minus square and t plus square both commute with -1 to the f. That's the thing we're doing the projection. But that begs the question that what happens to t tilde itself? What's causing us troubles for t tilde in doing the projection to the Ising Hilbert space is that t plus and -1 to the f do not commute. And that was the single most important minus sign, which signals an anomaly in the Majorana system we talked about before. Because of this sign, this operator t tilde does not survive the projection right here. It's not an operator acting on the projected Hilbert space. It would take you outside this projected Hilbert space. So how do we fix that? We simply don't have this t tilde in the projected Hilbert space. But one of the two guys is innocent. It's only t plus that's causing us trouble. Remember, t minus commute perfectly with -1 to the f. But one thing you can do instead is to define an operator d, again with an unimportant root 2 factor that I'm going to write here. You still put the innocent t minus up here, but you put a big 0 down here. T plus is giving us trouble. Let's just get rid of it. So now this operator is an operator acting on the projected Hilbert space. So I'm doing the projection. and you can write it as T tilde multiply by root 2 1 plus eta tilde. And this is the way to derive the operator D we talked about at the first half of the talk in the Ising model. It really comes from the Majorana translation symmetry, but setting one block, half of it, to be 0 because of the anomaly of the Majorana system. From this expression, you can immediately derive the algebra we talk about up here. And this D you see, when you multiply 2 of them, it's almost the lattice translation of the Ising, except that you have to multiply by a 1 plus eta. If you take this equation and you erase part of it, that has appeared in many references before. If you erase this part, that's the continuum fusion algebra we are all familiar with. If you erase this part, then this is the usual statement that Majorana translation is a half translation of the Ising model. But if you do it globally on a closed chain, you really have to have both. So in that sense, D is a half lattice translation, but it's non-invertible. One very important thing I want to emphasize, which is manifest from this expression, is that what is D dagger? D dagger is root 2 T minus inverse 0. And that is D times T inverse. So let me write it up here. D dagger is D times T inverse. That in particular means that D is not the same as D dagger on the lattice. This is drastically different from the continuum. In the continuum, this curly D is its own dagger. So we already see something qualitatively different between the lattice algebra and the continuum algebra. And that will have many important consequences that I won't talk about today. Finally, I'm out of time. So finally, let me comment on the relation to the continuum a little bit more. So as you take on the low line state, when you take n to infinity or to be large, then the D is related to the continuum operator D. So this is on the lattice. This is in the continuum. Times e to the 2 pi I p over 2n. So p is the continuum translation operator. In CFD, it's h minus h bar. And you see the important factor of 2 here means that this D, the lattice D, is really kind of a half lattice translation, but it's non-invertible. So we see that the continuum Kramers-Wenier symmetry, it comes from the lattice symmetry in this particular manner. This relation is exact without any further 1 over n squared correction. And in this sense, the continuum D is not an emergent symmetry. It doesn't emerge out of nowhere. Rather, it emanates from this non-invertible lattice translation of the Ising model. So I'm out of time, so I'm just going to conclude with this algebra on the lattice. And what I find really intriguing about this is that there's something fundamentally different about the algebra on the lattice versus in the continuum. And that begs for a different study of the lattice system compared to the continuum one. And I want to compare our algebra with many the other algebra in the literature. So there's a very nice paper by Assen, Fendley, and Mon in 2020, where they also consider the Hamiltonian lattice model, but they have the algebra D times D being 1 plus eta. So what they have is that they take the tensor product, sorry, I misspoke, the direct sum of the Hilbert space on the side and the Hilbert space on the length, each of 2n dimensional. On this direct sum Hilbert space, you can realize the symmetry algebra without mixing with the lattice translation. Whereas in our case, we as I emphasized throughout, we have a tensor product Hilbert space. So if you just compare these two cases, it's kind of interesting that if you have a non-tensor product Hilbert space on the right, then you can realize an internal non-invertible symmetry on a non-tensor product Hilbert space. But if you insist on the tensor product Hilbert space, then the non-invertible symmetry necessarily the non-invertible symmetry mixes with the lattice translation. I don't have a general proof or even an argument, but there appears to be some tension between having a tensor product Hilbert space versus having an internal non-invertible symmetry. And I think that begs for further study. All right, and sorry for running over time. I'll stop here.
Hey, thanks a lot. Are there any more questions?
Do you expect these last few statements to be like generic, true for other fusion categories?
No. It depends on the fusion category. So it is possible to realize some fusion categories internally on the tensor product Hilbert space. That's a very good question. That's something we are working on right now, indeed. Hi, Sal.
Hi, thank you for the nice talk. So I wanted to ask, here we saw that a duality defect came as an eminent symmetry emanating from translations. I would expect that's probably generally true, that anytime you have a lattice duality defect, it becomes an eminent symmetry in the continuum from translations. But do you think that's generally true?
I think it's related to Diego's question, that there are examples we are currently investigating where the non-invertible duality symmetry does not mix with the lattice translation.
I see.
It depends on the details of the fusion category. And let me also say that I think it's not even fair to call this a fusion category on the lattice, because it's simply a different algebra. And that begs for a thorough investigation on the lattice. Hi, Juban.
Yes. Hi, thanks, Shu-Heng, for the nice talk. So
thank you.
Get back to this U1 phase that is Ma8, that one. So I think here we only consider one Marana chain, is it? Oh, sorry.
No. This is
one Ising chain.
Yes.
And but you say it has something to do with the Ma-A anomaly for the maybe Marana chain, is it? Or ABK invariant?
Yes.
So can you say more because this n here is the number of sites, right?
Right.
Bosonic system, but you somehow say it's related to the
right. Because this operator, as I explained, the second half of the talk really arises from the Marana translation right here. So there's a question about how you pick the phase for T minus, the Marana translation operator on an anti-periodic chain. And that's something we discussed extensively in the paper. I probably won't have time to go over it in details, but the idea is that if you take T minus, so T minus can be written explicitly in terms of the Marana fermions. But if you compute T minus to the 2nth power in its naive form, generally you get a phase. And the phase depends on n, modulo 8 or modulo 16, depending on how you set up the problem exactly. So in the paper, we discussed possible phase redefinition of T minus, which can be viewed as choosing a counter term for the corresponding operator, if you think about it from the continuum point of view. And we argue that there is a natural choice of the counter term such that T minus raised to the 2nth power is exactly 1 here. And the fact that the mod A periodicity shows up comes from the fact that this Marana translation operator, when you compute this 2nth power in its naive form, you see an interesting mod A dependence on the n.
Okay, thank you.
Another question on this final point, the final point about the continuum limit, let's say, and this fact that as you explained, on the lattice, depending on whether you decide to double the Hilbert space or not, the symmetry obeyed by the D mixes or not with the space-time symmetries. But this distinction disappear in the continuum limit.
Right.
So what is the intuition behind this disappearing of this mixing with space-time symmetry in the continuums?
Well, it really depends on the case, right? So as I said, in the Ising case, the D mixes with the lattice translation, but there are other cases where you can have a lattice duality symmetry that's completely internal. And if you're asking me for intuition, one intuition which we are currently working on, is the fact that this D in the continuum has root 2 quantum dimension. And that kind of suggests that it's hard, if not impossible, to realize it on a tensor product Hilbert space completely internally. And the mixing with the lattice translation, I think is tied to that fact. But it really depends on a case-by-case study. You could also have examples where the quantum dimension is an integer, and yet it still mixes with lattice translation.
In the continuum, in the symmetry algebra, there will be never any remnant of of space-time symmetries.
That's right. That's right.
So it seems that on the lattice you can read more refined information directly from the symmetry algebra.
I don't think refine is the right word. I think it's just a different algebra. In fact, in many senses, which I'm purposely not going to say today, in many senses, it's less refined than the continuum.
Why less?
I'm going to plead at this point.
Okay. Sorry, another quick question. In the continuum, there is typically another claim about the relation between Majorana and Ising, that you can get the Majorana fermion starting from the Ising model by gauging the zero symmetry with the Arf invariant. What is the relation with what you explained?
That's exactly what we are doing here, but I structured the talk such that we don't have to talk about the continuum. Okay. This procedure is exactly what we do in the continuum bosonization.
So okay, I can view this as the lattice version of the continuum procedure of gauging with the Arf invariant.
Yes.
I see.
Yes.
Sorry, can I ask a question?
Yes,
Sure,
please.
Is this algebra that you are finding here with the translation and D compatible with some fusion category or not?
Well, that depends on what you mean by compatible.
In the sense that is compatible with the pentagon equations. Sometimes there are fusion algebras that are not fusion categories because they're not compatible with.
Okay, yeah. So that's an excellent question. So first, it's compatible in the sense that when you take n to infinity, t goes to 1. And therefore, this in the literal n goes to infinity limit, you can drop this term and you retrieve the continuum fusion category. That's the weakest sense of compatibility. But I think you are asking an even more interesting question, is that on the lattice for finite n, do you have some pentagon identity, or how is it modified? And that's something we're working on right now.
Okay, thank you.
And let me, sorry, at this point, just one quick comment. So you can already ask the question in the case of an invertible symmetry. There are many, there are many examples of continuum invertible symmetries that emanate from a lattice translation. And there you can also ask how, is there an analogous pentagon identity on the lattice? And this was beautifully done in a recent paper by Shu-Heng Shao. And I think there ought to be a non-invertible version of that.
Okay, maybe we thank Shu-Heng now, and then we can stop the recording and some more questions.
Thanks for all the nice questions.